Hi, my name is Himanshu Shukla. I'm a student of Chandigarh University, and today I'm gonna discuss about quantum computing. What is quantum computing? Quantum computing is when we use the laws of quantum mechanics and perform the computation using it. So what are those principles on which the quantum computing works? The quantum computer works basically on three laws of quantum mechanics. What are those? Let's talk about number one, that is superposition. Superposition is when a body can be in two states simultaneously at the same instance of time. Number two is entanglement. Entanglement is the property due to which an object is to be defined with respect to the other even though they are separated by a large distance. Number 3, interference. Well, talking about the interference, both constructive and destructive interference are used in quantum computer. How and when they are used? The constructive interference is used when we have to amplify the true values so that we would only get the true values. And what about the false values? The false values get cancelled out through the destructive interference. Now let's talk about what are the components of the quantum computer. How the quantum computer is made. The quantum computer consists of dilution refrigerator, qubits, microwave pulses and quantum chip. Dilution refrigerator is used to cool down the quantum chip to near about absolute zero or 10 to 14 millikelvins. Now, what are the use of that microwave pulses? Microwave pulses are used to control the qubits. How to control the qubits? The qubits are controlled in such a way that the amplification and the controlling the measurement, that what are the true values, what are the false values, how much is the frequency, and all the controlling factor is done by the microwave pulses. Now let's talk about the development and the use of quantum computer. Well, as I have told you that qubits are used in quantum computers. So when we are using the qubits, it's ultimately much more faster than the classical computer, because when we are using classical computers just flip-flop the bits, but in quantum computer qubits spin, and because of the phenomena of superposition, they can be zeros and ones at the same time. But in classical computer it is not possible to be both zeros and ones at the same time. In classical computer they will be either 0 or 1, but in quantum computer they will be both zeros and ones. So okay, it's fine, but what else can we get with that? We don't need quantum computer just because of speed. Yes, it's true. The other factor which comes into play is storage. Just to let you know, according to the vice president of IBM also has a quantum computer known as IBM Q. According to him, to represent a coffee molecule, it needs to take around 10 to the power 48 bits in classical computer. But if we would need to do the same task to represent the exact coffee molecule exactly same in a quantum computer, it would take around 160 qubits. Another interesting fact, to represent the data which can be represented by 200 qubits, it would take all the atoms of the universe to represent the same data in a classical computer. So okay, and the second thing which might come to the mind, that how to use this quantum computer. Well, although these quantum computers are in developing phase, but in early stages few scientists have actually discovered few algorithms like Shaw's algorithm, which works on basically factorization of numbers, and Grover's algorithm. But those are not the algorithms which can be used in the present, as they would need hundreds of thousands or nearly millions of qubits, and currently we have only 53 qubits as per Google's Sycamore or IBM's IBM Q or whatever we talk about. We have maximum 53 qubits. Well, if we are talking about Google Sycamore, let me tell you an interesting fact that Google Sycamore was the first quantum computer to reach the quantum supremacy. Now, what else can we do with that coffee molecule example which I have talked about? The coffee molecule example is that if we are able to represent a single molecule of coffee, then we could have the ability to modify its shape, to modify its structure. And what can we do with that? It might be possible then that in upcoming future you would be hearing that, hey, we have a coffee that tastes like a lemon, or we have a coffee that tastes like a chocolate. Isn't it sound funny? But it might be true in upcoming future. Well, all these things, if kept aside, if there are many of the advantages, then there might be few disadvantages as well. All the passwords, all the encryptions which are going on in this world are basically RSA encryption. But according to Shor's algorithm, it states that using quantum computer, we can factorize large numbers, huge numbers, which is the basis of all the encryption in this world, and also the RSA encryption. So even though that's far away, but then too we have to focus on building an encryption which should be quantum based on quantum. Moving forward, well, if we can surely do the we can work on Shor's algorithm, we can work on coffee molecules, we can work on such complexities in the world, but then too we are struggling to get more and more qubits in the quantum computer. So what can we do to solve this problem? Everybody is searching, as it is not so difficult to just add qubits. It is difficult to add the error corrected qubits. If the qubits are not error corrected, then there are chances that the data which we are trying to get from the quantum computer might get lost in between, and we don't want that, as it would take a lot of time to rebuild that same structure, to rebuild that same representation in the quantum computer. So what should we do to analyze this problem and to solve this problem? Well, we are trying to represent a coffee molecule in a computer. We are trying to represent anything on a quantum computer. We are trying to get solutions from the quantum computer. Then why aren't we thinking that a quantum computer should solve its problem on itself? How? Why, in simple language, if I say, why don't we try to ask the quantum computer itself, how can we increase the error corrected qubits in it? Why shouldn't it give its own solution rather than we searching for the solution? If we can use it in chemical industries, if we can use it in automation industries, if we can use it in any of the industries, then why can't we use it in the quantum computing itself? We should probably think of it. We should probably find out the ways in which how can we represent quantum computer into a quantum computer. Why shouldn't we introduce to a quantum computer that this is how you look like, this is what you are, and just search for the factors that how can you improve yourself. If it can give the solution that how can we improve ourselves, then it should absolutely give us the solution that how can it improve itself. That's all from my side, friends. Thank you and have a nice day.